So then our question is, if we're not changing our temperature by adding this energy, where is this energy going? If you take a look, where is this plateau happening? It's at 0 degrees Celsius. This one's at 100 degrees Celsius. So again, we're talking about water, so you know this is the melting or freezing point and our boiling point. So we're getting a phase change at this point. So we're adding energy to it, yet we are not changing our temperature, we're just changing phase. So it takes a certain amount of energy just to change the phase of the substance we're talking about. And we haven't talked a whole lot about intermolecular forces, IMFs, but at this point we have a solid. At this point we have a liquid. At this point we have a gas. Okay? In terms of the position of our molecules in a solid, they're fixed positions. There's an attractive force between the water molecules that are holding them in fixed positions in relation to each other. So they still have kinetic energy where they're kind of vibrating back and forth, but they're stuck in their positions. Eventually, when we get to this point, we get enough kinetic energy that can kind of overcome that. It'll start to happen at this temperature, but it's going to take some energy to overcome those attractions, and that's what's going on here. Same thing here. So at this point, we have solid and liquid in equilibrium. In this case, we have liquid and gas in equilibrium. So we're getting melting if we're going in this direction, freezing if we're going in this direction, vaporization if we're going in this direction, condensation going in this direction. Okay, and there's a factor, there's an equation for this too. It also has to do with energy, right? So Q is still part of it. We're adding energy. Okay, but there's something that's going to tell us how much energy it's going to take. Well, a similar factor, so mass is going to be part of it, right? If you have 100 grams of ice versus 10 grams of ice, it's going to take more energy to melt 100 grams. So mass is part of it. In this case, we had specific heat, which was specific to water. We're going to have another factor that's specific to ice at this point, what's called your heat of fusion. Okay, so at this point, from here to here, it's talking about our heat of fusion. So this is a value specific to ice. It tells us basically how much energy is required to melt a gram of ice. It's already at 0 degrees Celsius. Okay, and so for ice, that value is about 333.6 joules per gram. Okay, so if you know how much mass you have, and you know the heat of fusion here, you can figure out how much energy it's going to take to melt that. Notice there's no change in temperature, as we had in our specific heat equation, which is fine because we're not changing our temperature at this point. So temperature is not a factor. All the energy is going into changing the phase. Okay, and we have a similar situation when we go with vaporization. So up here, we're going from a liquid to a gas. Again, we're not changing our temperature. We're going to have Q to represent that. So we have Q is equal to mass. So mass is a part of it. It's going to take more energy to vaporize a higher mass of water. But we also have a different factor. So HV, which is heat of vaporization, this is going to be a larger value than your heat of fusion, which makes sense. If you look at this graph as it's drawn, it clearly takes more energy. This is the same mass of water. It takes more energy to vaporize it than it does to melt it. Okay, so this value is about 2256 joules per gram. So if you know what mass of water you have, you can figure out how much energy it's going to take to completely vaporize it. Okay, so if we're talking about an entire transition here, so we're going from ice at -50 to water vapor at some point over here, from here to here, it's going to be based on Q is equal to MC delta T. Actually, there's a different specific heat for ice than it is for water, but there is a value for it, so you could figure that out. It takes a certain amount of energy to change the temperature. From here to here, heat of fusion, so change of temperature is not a part, but the mass is important. From here to here, we're going for another specific heat. Here to here, heat of vaporization, and from here on, since we're changing temperature, it's going to be more specific heat. We could do all these different parts, figure out how much energy they would take, combined all that energy, the sum of all those energies, to tell you what it would take to go from this point all the way to this point.